Hello everyone, this is Avon, your controls hardware lead, and today I'm going to be covering an FSAE electric BSPD. Now, for the first thing, what is a BSPD? At the top here, BSPD is a brake sensor plausibility device, and the rules say it must be a standalone, non-programmable circuit to check for stimulus braking and high power output, so both of these together. It must be provided in addition to the apps, and it must open the shutdown circuit when these two exist. Demand for hard braking. The motor accumulator current is at a level where 5 kilowatts of electrical power in the DC circuit is delivered to the motor. It can have a delay up to half a second, and it must open the shutdown circuit when there is an open or short circuit in any sensor input, and we must test it. So to quickly break this down, essentially we need to create a circuit that'll take the brake and some way to measure 5 kilowatts of power and compare those two together to check if they're both happening at the same time, and if they both happen at the same time, we turn the car off. So we need to check for hard braking and 5 kilowatts of power. Then we also can put a delay on it, and lastly, we need to make sure that if any of the sensors used have an open or short circuit, that it will also open the shutdown circuit. So first things first, we need to talk about how to get the braking and power. So we do that with sensors. So our brake sensor, this is essentially, it's like a potentiometer on the brake, and as you push the brake further and further down, it'll increase the voltage on the sensor output, and the voltage will increase. It will start at around 0.5 volts, and it will go up to like whatever, 1.1, 1.2, and it also depends on how it's tuned. So then we have the current transducer. This is for measuring power. The current transducer uses the Hall effect. If you're not familiar with the Hall effect, you can Google it and figure it out of curiosity, but for now, don't worry about it. So it'll use the Hall effect sensor will basically create a voltage proportional to the current going in the wire. You'll have some current going through your high voltage wire. It'll sense a voltage on it based on that current, and then you can look through the data sheet, multiply those two values together, and you'll be able to find the power. So you can get a voltage that'll mean some power. Okay, so now we have to use those two things, but first you need to boost the logic, because we're working with things on like the volt, like a singular volt range, which doesn't usually work for digital circuits, as MOSFETs won't be switched. You'll lose voltage throughout the line, so we just need to boost that. To boost that, we will use a comparator. So here we have our brake, which is our voltage source, and we have a voltage step function that will go into potentiometer. We use a step function just to signal like you turning it on, like just the second you flip the low voltage switch, and this will go into the comparator. And then when the brake is higher than the potentiometer, you'll get an output here. This is essentially the basic idea of what we're going to do to boost the voltage, but the one issue we run into this is it doesn't protect against open or short circuits. If our brake were to be an open circuit, meaning it would show 0 volts on it, that would be okay. It would be a low, but if it were to be a short circuit and it would show 5 volts on it, it wouldn't be okay, because you would get an output saying something you do not want it to say. So we can use that open and short circuit protection using this circuit. Essentially, you can use two comparators and use them like an AND gate. So if we look here at this circuit, we need to decode what's happening, because first of all, we are usually just told that if the non-inverting input, the positive side, is higher, it'll produce the voltage at the positive rail, the VCC over here. And if the negative side is higher, it'll put out the ground. In reality, there are some comparators work like this, but not all comparators. We are going to use an open collector comparator. An open collector comparator essentially means that the output of the comparator is left floating when the non-inverting input is higher. So for this case, if the positive side was higher, the output here would be left floating. If the output is left floating, we can make it act like an AND gate. So how this works is first we have to look at the biased inputs. These are the inputs that have just a set voltage using a voltage divider. So first we have this one. This is for the potentiometer. This comparator is going to be checking the high. So we are going to be checking for the highest value. This would be the hard braking, or would be when 5 kilowatts of power. And that is what we would tune this to. We would tune it so it would be usually just below it, like a couple millivolts below it. And you would tune this potentiometer. So I'll use the brake sensor as an example. Let's say this was like 1.5 volts. And we said this is when it's hard braking. And if this was hard braking, then it would depend on what the brake is doing. So next we have this input over here. This is also biased. So you can see it as 100 k ohms here, 10 kilo ohms here. This will create a voltage divider and it'll put about 450 millivolts here. So this is like your minimum because the brake sensor will always stay at about 0.5 volts. And if the brake sensor were to be opened, it would show 0 volts and it can't go below 450 millivolts. Sorry. Now we have our high side and our low side. So now we're going to start putting an input. So let's say our brake was an open circuit. Let's say we saw 0 volts here. So there'd be 0 volts here and 0 volts here. So first, the low comparator, we see that the minus side is the one that's higher. This means that the output here would be grounded. That means we're seeing 0 volts at the output node, meaning that the MOSFET would then allow current to flow through it. The next case we need to check is when the brake is at a normal voltage. That would be like, for example, when the brake is not being pressed at all. This would output 0 volts. We then see 0 volts at both comparator inputs. First, let's check the low comparator. We see on the low comparator that the non-inverting side, the positive side, is higher, meaning this would be left floating. We also see on the high comparator that the 1.5 volts at the non-inverting input is also higher, meaning this comparator is floating. If both comparators are flowing, the output is not grounded. And we would see 5 volts here. This is because we are going through this resistor into the MOSFET. And remember, the gates of the MOSFETs are like capacitors, so they will be like open circuits. And that means we would see maximum voltage here. This would then not allow the current to flow through the MOSFET, removing current through the load. Now, for our last condition, we are concerned with if the sensor is then showing 5 volts, which it would show if it's shorted. So we would see 5 volts here. That means 5 volts at both inputs. So the bottom comparator, of course, would be floating because the non-inverting side is higher than the inverting. The top comparator, the non-inverting side here, is higher than the inverting side here, meaning we would see ground here. This means that current would flow through the MOSFET, meaning we would see an output. Now that we understand how this comparator circuit works, we can then move on. If you ever want to come back and look at it, the slides will have all of the conditions, and these will be in the description of the video. You can look here if you ever forget. We now repeat this for 2 sensors. So you would have 4 comparators in total, and you would use 2 8-pin comparators to put that on a PCB. Now that we're done with that, we need to do the stimulus part. It needs to check for demand for hard braking and for 5 kilowatts at the same time. It's like if you were to press the accelerator and the brake at the same time. So to do that, we can make an AND gate using MOSFETs. This is one way to make an AND gate. You could also just make a digital AND gate. We can think of this just like any regular AND gate. If I were to put 5 volts here and 5 volts here, the P MOSFET would not allow current to flow, and this P MOSFET would also not allow current to flow. If I put 0 volts here, current would be able to flow through this one, but because the MOSFETs are connected in series, this one would stay closed and no current could flow. But if they were both 0 volts, they could flow through both of them. And this is a simple way you can create an AND gate. Now that we understand the AND gate, there is one more subcircuit we need to cover. This is the delay and output logic boost. The delay is there because in the rules it states the BSPD may delay opening the shutdown circuit up to 0.5 seconds to prevent false trips. Of course, if we were to press the brake down a little bit while there's still being power delivered to the motor, we wouldn't want it to instantly turn off. We would want it to wait for a check. A simple delay circuit is usually made using an RC circuit, which you can see below. This is something I will cover in a different video. If you want to solve it for yourself, for a if you wanted to figure out for yourself, you would use the step response equation, you would solve for time, you would bias the comparator to specific voltage, and then once the capacitor reaches that specific voltage you're looking for, so if in this case it's around like 4 volts, 4.2 volts, this means the output would then be grounded, and if the output is grounded, this means there is a fault. The last part of the circuit, the faulting part, is done by the reset latch and not by the circuit. This line would then just go to the reset latch. The very last thing, we have an extra circuit that will provide protection for the inputs of the comparator. The input of the comparator is usually a MOSFET. These MOSFETs can be fragile if the inputs to them are very long. So if it's coming from a sensor, you're running a couple feet of wire to move through the car and then would come into your comparator. The problem with this is that that line is very susceptible to both electrostatic discharge, ESD, or electromagnetic interference, EMI. So you want to protect your comparator input so you would not get any false trips. To protect this, there's a couple of things we have here. First, we have a 100 kilo ohm pull-down resistor. The pull-down resistor provides a couple of functions. First, it allows it to discharge a capacitor that is also used for decoupling, but it also helps to protect the input. It protects the input by not leaving that MOSFET floating. Next, you have is a 10 kilo ohm ESD protection resistor. This is used to protect the internals of a comparator because a comparator usually has ESD protection through diodes that will go through the inputs and point to their ground and point to the VCC voltage. The resistor protects this by protecting the diodes from high amounts of current because ESD is essentially 2 to 8 kilovolts of voltage that will last for an extremely short amount of time, but if they last even a little bit too long, the amount of current can fry the diodes inside the comparator. To protect this, you can use an extra resistor, which will protect your input. And next you have is a 1 nanofarad capacitor. This acts as an RC low-pass filter and helps to filter out electromagnetic interference like magnetic fields above kilohertz range of frequency. The very last thing are TVS diodes. In the diagram are 2 Zener diodes, but in reality you would use a bidirectional TVS diode pointing to ground. This would help shunt away any other voltage protecting your input. If you want to look more about this, you can Google it. Anyways, this is the last thing for a BSPD. If you have any questions, you can ask in the comments. You can Slack me, and I will be happy to get back to you. Thank you.